Hi gang, and welcome back to Analyzing the Universe. Last time we left G.K. Purr in the precarious aftermath of an explosive state. But the story gets even more interesting because during these infrequent minor outbursts every 3 years or so, the object starts emitting copious amounts of X-rays and does so in a very special way. So let's head back to DS9 and see what we can find out. So we open DS9 again. We're going to look now and see what those X-rays look like. Go to Analysis, Virtual Observatory, Connect using Web Proxy, Rutgers Primary MOOC, Observation number 3454, click on the title. There it is. Now we're going to look at the light curve. So we go to Analysis. Let's cut off things here. Bring that over here. Go to the Chandra Ed Analysis Tools. Cut that off. Bring it over here. And click on F-Tools Light Curve. Plot the light curve data. And there it is. Boy, that looks like it's bobbing up and down here. Maybe one peak here, two peaks there, another one there. But does it have a regular period? Let's zoom in. Let's take our crosshair, and if we click anywhere in there and hold things down, we can drag a smaller area, and there it is. And look at that. Things are going up and down. And it looks like maybe 1, 2, 3, 4, 5, 6, 7 peaks or so in about, I don't know, 2,000 seconds. Man, this isn't very precise. Can we do better than just this eyeball method? Fortunately, mathematics comes to our rescue with an immensely powerful tool called a Fourier transform or power spectrum. Let's see how this works. You can imagine that it would become quite tedious to figure out by hand what the period of variability of an object might be, or indeed whether it even exists at all. But let's see how mathematics can come to our rescue. First, imagine a light curve, which is a plot of intensity versus time that looks like this. It's easy to see that a sine curve can come pretty close to duplicating the data. Now, what if our light curve looks like this? Still no problem. We can get a sine curve that matches pretty nicely. But what about a constant intensity source? Something that looks like this. Well, a moment's reflection will tell you that a sine wave of zero frequency or infinite period will have precisely this property. Remember that f, the frequency, is 1 over the period. For example, if the sine wave has a period of 1/3 of a second, then it will bob up and down 3 times in 1 second. And if something happens, say, 7 times a second, its period is 1/7 of a second, and so on. But now, what if our light curve looks erratic, as all real light curves will? The incredible thing is that any light curve, no matter how bizarre it looks, can be fit exactly by a bunch of sine curves of different frequencies added together with different amplitudes. It's a miracle, really. This transformation of an arbitrary curve into sinusoidal components is called a Fourier transform, or a power spectrum. Entire books have been written on this topic, and rightly so. Let's see what the Fourier transform, also known as a power spectrum, of our various examples might look like here. In the first one, you see we just have one frequency, and therefore there will be 0 amplitudes for all frequencies except that particular one. In this example, the same thing is true, except the frequency is much higher. So in that situation, everything will be 0, with the exception of a higher frequency. Now, it turns out, if you're really sharp, you'll see we made a slight error in that situation because there is a constant amplitude upon which these two sine waves have been superimposed. So there really is going to be a 0 frequency component in every single light curve that we examine. And that will represent the part of the light curve that is basically constant in intensity, upon which a certain amount of the emission will be periodic. In this case, all we have is that constant intensity component, and so our Fourier transform would have a 0 frequency component and nothing more. Now, in this particular case, you can see that we're going to need a big mixture of different frequency sine waves, so our Fourier transform might look something like this. And it might be very hard to tell whether or not there is any periodic component in this particular data. So now that we have an understanding of the basics of this type of analysis, let's return to DS9 and look at the power spectrum of real data in the form of X-rays emanating from GK Per in the year 2002. Okay, back at DS9, we look at the Chandra-Ed analysis tools again, and now, after running our light curve and finding out what a power spectrum is all about, let's click on that power spectrum. Plot power spectrum data. And here it is. All of the amplitudes or power of all of the sine wave frequencies necessary to exactly reproduce our light curve. Let's zoom in and see it in detail. We are obviously going to be interested in this area of our power spectrum here because that's where all the action is. So we click around here and extend our box up over here, and now you see, after zooming in, we have a frequency near 0, which is probably that constant part of an intensity source that might be just steady, and another one that is at about between 0.002 and 0.003 cycles per second. So let's zoom in again here and see what it looks like. Now you can see that we have a very, very strong peak at about 0.00284 hertz, or cycles per second. Well, 0.00284 cycles per second translates into a period, and you should work this out, of about 352 seconds. Now we can do something really cool. We can fold all of our data modulo this 352 second period and put all the maxima and minima of all of the up and down parts of the light curve on top of one another, add them up, and see what the overall structure of the light curve looks like. Let's do that. We have a period fold. We enter the value of a period of 352 seconds, and we're going to divide that light curve into 25 little sections. So there'll be 25 little pieces of total length, 352 seconds, and we're going to fit the entire light curve into that particular display. So we say OK, and look at that. There it is. The folded light curve of GK per bobbing up and down. You say, wow, it's just doing nothing but going up and down. But now notice the y-axis here. The y-axis has automatically been scaled to include the entire observation. It doesn't go from 0 brightness all the way up, but just from about 0.85 brightness units on up. So let's do this a little bit more legitimately. Let's go to Graph, and we click on Range. And when you do that, it brings up a little box that allows you to change your X and Y axes. Let's change our y-axis so that it starts at 0 instead of 0.85 and goes up to, oh, it looks like about 1.2. We'll keep that. We uncheck automatic so that we are actually doing things manually here. Click on OK, and now you see what the light curve of GK per actually looks like in its average. Okay, pretty cool. Now let's do something interesting. Let's see what happens if we use the wrong period, a period that really doesn't match the actual periodic change in GK per. By the way, before we do that, notice these little red tick marks here. That represents the error bars associated with each one of the assignments of these measurements to the intensity of GK per. You see, it's impossible to fit a straight line to this data. The error bars are too small to allow that. So we really have uncovered a truly periodic component to the X-ray emission of GK per. So now we're going to look at a period fold for a quote-unquote wrong period. Let's get rid of this. Let's do it again. And now instead of 352, we're going to put in 360. We hit OK. And, oh man, does this look grotty, doesn't it? But again, you see here we've got our y-axis is scaled very strangely. So let's go to Range. And once again, we'll start the range at 0 and go to 1.2, which I think we did before. Unclick automatic and OK. And look at that. With the wrong period, it looks like truly there is no periodic component. And you see, you ought to be able to fit a straight line fairly nicely through all of this data. What is happening in this case? Well, I want you to figure this one out on your own. And if you do, you will learn a lot about spectral power spectrum analysis and Fourier transforms. It's really interesting that if you just make a small mistake, a small error in the assignment of your period, you can get something that is very, very different from your periodic component. And this is, in fact, why we think that there really is a periodic component to GK per at 352 seconds. Now, we can ask a question, does GK per do this all the time when it emits X-rays? What about some other times when it might be bright in the X-rays? Let's go to the discovery data that was made with the Exosat Observatory in 1983. So we click on DS9, click on Analysis, Virtual Observatory, connect using web proxy, Rutgers MOOC. And now, if you look, we have preloaded here a non-imaging observation of GK per. And we click on that and look at this. All you see is something just gray. And the reason we display it this way is that there is really no image. Remember, we talked about image formation a long time ago, a couple of weeks ago. And so our Exosat observation just looks like a grayish kind of blob. But there are X-rays in there. And let's see what happens when we look at them. We can go to Chandra Ed Analysis Tools. Let's cut this off here. Whoops. Oh, we can't do it that way, can we? We've got to first cut it off over here under Analysis. Then we can cut it off over here under Chandra Ed. And let's do the same deal. Let's look at the light curve. Plot light curve data. And now you see GK per possibly going. It's definitely varying, but is it periodic? Well, let's zoom in a little bit over here. Oh, look at that. 1, 2, 3, 4, 5, 6, 7, 8 maybe. 8 in about 2,300 seconds or so. Hey, that's pretty close to 300 seconds, 350 seconds. But once again, we know we can do better than this. Let's do a power spectrum. We do our power spectrum, and there it is. Let's zoom in. Whoops, let's grab it this time. And zoom in again. And you see, there it is at 0.00283 or 4, exactly the same frequency and therefore same period as we saw from the Chandra satellite almost 20 years later. So now that we've got the power spectrum, let's look at the period fold. We click on period fold. We enter the same 352 second period, 25 little segments. Let's do that, and here we've got it. Let's go to graph, range. We're going to rescale the y-axis from 0 to about 1.5, uncheck automatic. Okay, and there we have it, gang. The X-ray periodicity of 352 seconds that was figured out or discovered by the Exosat Observatory in 1982. The same thing was happening then as seemed to be happening in the year 2002 with Chandra. So what can this be? What is going on? Let's go back to the blackboard and see what we can find out.